So now we know enough to be able to calculate the steady state probabilities in a queuing system or for a birth death processes, which is basically the umbrella that also covers the queuing systems as well. So let's look at the general queuing system. So we are going to basically extract the steady state probabilities for a general queuing system. Then we can customize the formula for any specific queuing system that we are going to look at. So for a general queuing system, this is the rate diagram that we developed initially, right? Obviously, it's a queuing system. Then the possible values for the state of the system is 0 entities in the system, 1, 2, 3, all the way to infinity. And we assume that in a general scenario, the rate of arrivals to the system depends on the number of entities in the system, and the rate of departures from the system also depends on the number of entities in the system. That's why I use lambda 0, lambda 1, lambda 2, all the way to lambda infinity, as well as mu 1, mu 2, mu 3, and so forth. So we can say that for any queuing system, entities come to the system, entities leave the system. So we go from any state j to j plus 1 to j minus 1. So all this transition happens over time. But in the long run, in the equilibrium, in the steady state, the expected number of departures from any state j equals to expected number of entrances or arrivals to the state j. So that's the rule that exists in any queuing system. So average number of times that we get into any state. So for example, for state 2, these are the arrows that enable the system to get into system 2. So average number of times that the system has gotten into state 2 from any possible arrow equals to the average number of times that the system has gotten out of the state 2 through any possible arrow. This is what this statement is. So now let's write this rule for the possible states in the system. So let's look at the state 0. So for state 0, average number of times that we leave state 0. Obviously, when we are at the state 0, we are going to leave the state with the rate of lambda 0, okay? So, however, this is not happens all the time. It happens when we are at the state 0 with the probability of pi 0, right? So then the average number of times that we leave state 0 is basically if we are at the state 0 pi 0 with the rate of lambda 0. That equals to average number of times that we have entered the state 0. And entering the state 0 happens with this rate mu 1, but it happens only if we are already at the state 1. Then we use this rate to enter state 0. And so if we are at state 1 with probability of pi 1, then we can get into state 0 with the rate mu 1. Okay, so now this can help me to find pi 1, which is pi 0, lambda 0, mu 1. How about state 1? For state 1, I can depart this state through these two arrows, right? This one and this one. So, and this happens if I'm at the state 1 with probability of pi 1. So I can depart these states if I'm at state 1 with the rate of lambda 1, or if I'm at state 1 pi 1 with the rate of mu 1. These are the two branches that would allow me to leave state 1. And how about the expected number of entrances to state 1? The entrances happens through this arrow. So this arrow and this arrow. So this top one happens if I'm at the state 0 with probability of pi 0, and this bottom one happens if I'm at the state 2 with probability of pi 2. So the average number of entrances to state 1 is if I'm at the state 0 with probability of pi 0, and then lambda 0 is the rate of going from state 0 to 1, or plus if I'm at the state 2 with probability of pi 2, and then I go to state 1 with the rate mu 2. Okay, so now if I already know the probability of pi 1 and just put pi 1 based on this formula in this part of the second equation, then I can find pi 2 to be equal to pi 0, lambda 0, lambda 1 over mu 1, mu 2. Let's see what if I write this equation for state 2. So for state 2, the rate of departures from state 2 is basically if I'm at state 2 and then I leave with the rate of lambda 2, or I'm at state 2 and then I leave with the rate of mu 2, and equals to average number of entrances to state 2. So entrance to state 2 happens if I'm at state 1 and then I enter with the rate lambda 1, or if I'm at state 3 and then I enter with the rate mu 3. So if I put a value that I found for pi 1 here in this part of the formula, and the value that I found for pi 2 here in this part of the formula, and I do the simplifications, then here I would find that pi 3 equals to pi 0, lambda 0, lambda 1, lambda 2, mu 1, mu 2, mu 3. And that's going to be how I'm going to calculate the probability of pi 3. And just note that in all of these, the values of lambda 0, lambda 1, all the way to lambda infinity, we know those because we said that for any queuing system to be able to analyze it, we have to know that rate of arrival to the system. And for the mu's also, we know those because we said for any queuing system to be able to analyze it, I need to know the service rates or the rate of the departures from the system. So the values of the lambdas and the values of the mu's are the ones that are given to me. So I know those part of these equations. What I need to find out is the steady state probabilities, or pi j's, which shows the probability that in the long run or in the equilibrium or in the steady state, the system is in the state j. Pi 0, the probability that in the long run there are 0 people in the system. Pi 1, the probability that in the long run there is 1 person in the system. So those are the unknowns that I need to calculate. So if I just continue this finding for each state, this is the general formula that I can write. For any state j, I can write that probability of pi j is going to be pi 0 multiplied by lambda 0, lambda 1, lambda 2, all the way to lambda j minus 1, mu 1, mu 2, mu 3, all the way to mu j. And as I said, this part of the formula is known because we know the values of all the lambdas and the mu's. I'm going to name this with Cj. So this is a constant, and I'm just going to call it Cj. So as a result, pi j is going to be pi 0 Cj. So for any pi j, as you can see here, I know the value of Cj, obviously, because as I said, that's based on the lambdas and the mu's, which are known to us. So the value of the Cj is good and is known. I have to find out the value of pi 0, because if I know the value of pi 0, I'm going to just multiply it by Cj, which is known, and then I can find the value of pi j for any possible state in a queuing system. So my challenge is to find the value of pi 0. So how can I do that? One thing that we know about any stochastic system, and a queuing system being one of those, is that the sum of the steady state probabilities is 1, right? That's something we know about any stochastic system, because in the long run, in the steady state, the system is finally at one of these states, 0, 1, 2, all the way to infinity. So the sum of the steady state probabilities is 1. So that means if I write the values of pi j, so that's pi 0 plus pi 1, based on this formula that we have here, is C1 pi 0, pi 2 is C2 pi 0, pi 3 is C3 pi 0, all the way to infinity equals to 1, right? So now I can take pi 0 out, so this is going to be pi 0 multiplied by 1 plus C1 plus C2 plus C3 plus all the way to infinity equals to 1. I can write this as a summation of the Cj, the sum of the Cj. J is going to go from 1 to infinity. As a result, pi 0, which is the one that I want to find, is 1 over 1 plus sigma Cj, j from 1 to infinity. And again, remember that the value of Cj's are known because the value of Cj, which is specified here, are based on the lambdas and mu's that we know. So the Cj's are known. So basically in this formula, everything is known. As long as this infinite sum of Cj's from sum of basically C1s to all the way to C infinity, as long as this sum is returning a finite value, pi 0 exists. And if the pi 0 exists, I can put it in this formula and I can calculate the pi j for any queuing system. In other words, the steady state probabilities for that queuing system exist. Okay, so that's basically how we can calculate the steady state probabilities in any queuing system.